For decades, scientists could only glimpse Yellowstone's hidden heart as a blurry amorphous blob, with no certainty whether the magma lay 3 or 8 kilometers below. That all changed in April 2025, when a 53,000-pound vibroseis truck and hundreds of sensors produced the first sharp seismic image, revealing a volatile, rich cap just 3.8 kilometers down. The study, led by Rice University, the University of New Mexico, the University of Utah, and the University of Texas at Dallas, shows 86% solid rock threaded with pressurized gas and melt. Brandon Schmant calls it Yellowstone's steady breathing. But United States Geological Survey scientist Mike Poland warns that the ramifications for how we perceive volcanic hazard are profound. Yellowstone's last super eruption was 1,000 times more powerful than Mount St. Helens. Will this discovery change how we live with the world's most unpredictable supervolcano? Or is there something even deeper we have not yet understood? To examine the stakes and the science, subscribe and join us from the very beginning. Yellowstone's hidden world has always been shrouded in uncertainty. For years, scientists relied on indirect signals, earthquake waves, subtle ground shifts, and magnetic anomalies to sketch what lay beneath the park. But these tools could only outline a vague, shifting shape. The magma reservoir appeared on their screens as a blurry smear, an amorphous blob whose true boundaries and depth were lost in the noise. Estimates for the top of the chamber bounced between 3 and 8 kilometers down, a spread wide enough to mask almost any scenario. This lack of clarity was not just a technical nuisance. Without a sharp image, there was no way to gauge how close the molten rock and pressurized gases really sat beneath the surface, or how quickly conditions might change. The best models were built from scattered earthquake paths and low-resolution tomography, producing a picture as fuzzy as a shadow in fog. Every attempt to refine the image ran into the same wall. Natural earthquakes did not provide enough detail, and the methods available could not cut through the complex geology. The gap between what scientists wanted to know and what the data could actually show became a source of constant frustration. Yellowstone's greatest threat remained hidden, not by secrecy, but by the limits of the tools meant to reveal it. On a string of cold nights in 2020, the park's silence broke beneath the weight of a 53,000-pound vibroseis truck. The team, drawn from Rice University, the University of New Mexico, the University of Utah, and UT Dallas, moved methodically along Yellowstone's Grand Loop Road. Each stop brought the truck's steel plate down to the asphalt, sending carefully tuned low-frequency vibrations deep into the earth. More than 650 seismometers spaced every 50 meters listened for the faint echoes bouncing off hidden layers below. These artificial pulses, far weaker than Yellowstone's smallest natural quakes, traced a path into the crust that natural earthquakes never could. For months, the operation unfolded almost entirely at night. The team worked in darkness to avoid disturbing wildlife and visitors, their progress tracked by battery-powered sensors and GPS clocks. On one tense night, a sudden microquake and a cascade of equipment failures nearly derailed the run. But the field crew adapted on the fly. Every byte of data was precious, destined for the hands of geophysicists who would spend years refining the signal. Then, in April 2025, the breakthrough came. Published in Nature, the seismic image revealed a sharp, volatile, rich boundary at exactly 3.8 kilometers beneath the surface, resolving decades of debate over the magma chamber's true depth. For the first time, the top of Yellowstone's hidden reservoir was no longer a guess. It was a measured fact, credited to the collaboration of 4 universities and the relentless drive to see clearly underground. Beneath Yellowstone's surface, the seismic image reveals a structure both solid and volatile. At exactly 3.8 kilometers down, a sharply defined layer stands out, a cap that is 80 to 100 meters thick, and that acts as a boundary between the upper crust and the deeper magma reservoir. This cap is not a pure block of molten rock, nor is it a hollow chamber. Instead, it is a dense crystalline matrix, 86% solid rhyolitic rock, locked together in a rigid framework. The remaining 14% is pore space, but even this is split evenly. Half of those microscopic pockets are filled with molten silicate melt, and the other half with supercritical gases, mainly carbon dioxide and water vapor, compressed under immense pressure. This configuration was measured using amplitude variation with angle, a technique that analyzes how seismic waves reflect off the cap's interface. The result is a precise breakdown. 7% of the cap's volume is melt, 7% is gas, and the rest is hard rock. The numbers are confirmed by error analysis, with porosity measured to within 1.5% and the depth fixed within 30 meters. Beneath this volatile-rich LIED, the reservoir stretches out for 55 miles in length and 30 miles across, dropping nearly 10 miles deep into the crust. Most of this space is not a bubbling cauldron, but a mush of mostly solidified rock, with only 15 to 20% melt distributed through the mass. The true danger and dynamism are concentrated in that thin cap, where gas and melt coexist in a delicate balance. These proportions set the stage for everything that follows: the slow escape of gas, the steady venting through geysers and hot springs, and the potential for pressure to build if that release ever falters. Gases rising from Yellowstone's magma cap do not just vanish, they travel upward, threading through cracks and fractures and escaping through the park's famous geysers, mud pots, and steaming vents. This slow, constant leak acts like a pressure valve, letting the system exhale. Brandon Schmant, the lead author of the Nature study, calls it Yellowstone's steady breathing. In his words, the sharp boundary at 3.8 kilometers tells us that the system is venting efficiently. It is a volcanic pressure release valve rather than a sealed bottle waiting to explode. The cap's structure controls this breathing. As long as gases can escape, pressure stays in check. But if that release slows or stops, the balance can tip. Scientists track 3 warning signs. First, ground uplift greater than 5 centimeters per year. Second, earthquake swarms with magnitudes above 3. Third, gas emissions, especially carbon dioxide and sulfur dioxide, spiking more than 50% above normal. Right now, all these measures are well below the thresholds for alarm. Mike Poland from the Yellowstone Volcano Observatory puts it bluntly. The cap is like opening a can of soda, so the carbon dioxide rises to the surface and is released gradually, rather than building up until it explodes. It is a vivid image, but it comes with a warning. If the system's breathing ever falters, if gas cannot escape, the pressure could rise quickly. That is the credible failure mode, not a sudden out-of-nowhere eruption, but a gradual shift in the cap's ability to vent. Monitoring these small changes is what separates a stable volcano from one edging toward hazard. Yellowstone's record of destruction is written across the continent. 2 million years ago, the Huckleberry Ridge eruption unleashed more than 2,500 cubic kilometers of ash and rock, an event over 1,000 times the size of the 1980 Mount St. Helens eruption. Ash from that blast settled across a third of North America, with traces stretching from the Pacific Northwest to the Atlantic coast. The caldera formed, then spans nearly 45 miles, a scar visible from space. Another eruption, Mesa Falls, struck 1.3 million years ago, ejecting hundreds of cubic kilometers of material and leaving ash deposits as far as the Gulf of Mexico. The most recent super eruption, Lava Creek, erupted 640,000 years ago, blanketing the Midwest and pushing fine ash into Louisiana's ancient sediments. Each of these explosions released vast clouds of sulfur dioxide, forming high-altitude aerosols that dimmed sunlight and cooled the planet by up to 2 degrees Celsius for years. The scale of these eruptions dwarfs any modern disaster. It forces a reckoning with the power still locked beneath Yellowstone's surface. With a sharp seismic image in hand, Yellowstone's risk assessment moves from speculation to measurement. The 3.8-kilometer cap now serves as a baseline, a reflector that can be checked for subtle changes over time. Monitoring is not just about watching for earthquakes or swelling ground anymore. It is about tracking the behavior of the lid itself. If the cap's reflectivity shifts or if gas venting patterns change, scientists have a precise metric to flag early warning signs. This approach shapes where new seismometers are placed and how resources are allocated, focusing on the narrow zone that truly matters. The same vibroseis and dense array method is already being considered for other supervolcanoes, from California's Long Valley to Italy's Campi Flegrei, making it possible to export Yellowstone's model worldwide. For policymakers, the evidence-based clarity means funding can target the most revealing measurements rather than scattershot surveillance. Science at last has given us a way to reduce uncertainty, turning a once blurry mystery into a system that can be watched, measured, and, when needed, acted upon. Yellowstone's magma cap stands mapped at 3.8 kilometers, 86% solid, yet laced with volatile gases that govern its every breath. This seismic clarity reshapes how the world faces supervolcano risk, not with certainty, but with vigilance. Our understanding deepens, but the stakes remain immense. Subscribe for more revealing investigations.